All right, good morning, good afternoon, good evening, wherever you are. Welcome to plenary session 11A of FRB 2021, which will be about probing the magneto-ionic medium between us and fast radio burst sources. I've been particularly looking forward to this session because it's something that's very close to my heart. We have a great program of speakers, which we'll get to shortly. Just a reminder, if you have questions during the session, please use the Q&A button that's in the Zoom window, and I will field those questions to the speaker. And if the speaker is not available, because we have a couple recorded talks in this session, then please post your questions in Slack, or if you post them here, I'll make sure that they get to Slack so that the speaker or one of their collaborators can deal with answering those questions afterwards. Or if you're a collaborator of one of the speakers who's not able to be here live, then please raise your hand and I'm more than happy to unmute you if you want to field a question. Just let me know. I'll just very briefly mention, also keep an eye out, Manisha Kalib is going to advertise FRB 2022 in the general Slack channel pretty soon. And we'll bring this up tomorrow as well. So if you've enjoyed FRB 2021, then please keep an eye out for FRB 2022. Even if you haven't enjoyed FRB 2021, keep an eye out for FRB 2022 because I'm sure it'll be a fantastic symposium. It'll be held during the IAU in Busan, Korea next year, hopefully live or at least hybrid. So without further ado, I think we're ready to start the session. Our first speaker, could you share your screen, Alvina?
Yes. Okay.
Our first speaker is Alvina On, who will be talking about probing the magnetic universe with fast radio bursts. Take it away.
All right. Thank you, Jason. So first of all, thank you to the organizers for giving me this opportunity to talk today. And I'm Alvina, and I recently obtained my PhD degree from UCL, and I will be starting a postdoctoral position in Taiwan in a few months' time. So as you can probably see in my background, I'm currently in very, very sunny Brunei. So it's a really tiny country in Southeast Asia, and I'm working from home like many of you. So in the last 2 weeks, we heard several talks about how magnetic fields are important in the context of FRBs, possibly playing an important role in the physical mechanisms and the emission mechanisms. So today I will share a little bit about how we can probe the magnetic universe with FRBs acting as cosmological lighthouses. So we know that magnetic fields are everywhere around us, but the elephant in the room is, where did the first magnetic fields come from? And how do they evolve with the structure formation of the universe? And the reason why it's challenging to study magnetic fields is because it's simply invisible to the eye, and we can only infer their existence and properties through indirect methods. And here in the background of my slide is the beautiful Northern Lights, which is a wonderful evidence of the Earth's magnetic field interacting with solar wind. So if we move on to larger scales than the sun and the Earth, the galaxy that we live in is also magnetized, as well as larger scale structures such as nearby galaxies and galaxy groups. However, when we move to bigger scales, like for galaxy clusters and beyond, it becomes more difficult to see and measure the magnetic fields because they're simply a lot weaker. However, it is important to correctly infer the magnetic field properties at such large scales because they may hold some evidence of the first magnetic fields. Now, the question is, we still don't know whether the first magnetic fields is primordial in origin, meaning they're generated soon after the Big Bang, or maybe they're generated through some astrophysical processes after the first stars and the first galaxies form. So some numerical simulations like the one I'm showing on the left here, and radio observations of nearby superclusters and cosmic filaments roughly constrain the seed magnetic field strength to be roughly the order of nanogauss. So most of you have probably seen this equation before, and we know that the magnetic field is usually measured using the rotation measure at radio wavelengths. So by definition, the rotation measure quantifies the amount of rotation that occurs when the polarization plane of light rotates in a magnetic field. So observationally, we obtain the rotation measure by measuring the change in the polarization angles on the sky at various wavelengths. For example, the coma cluster here. So on the left, we can tell that the intracluster medium is magnetized through the detection of diffuse megaparsec scale radio contours here in green. And if we use bright polarized radio sources behind the cluster, we can fit polarization angles against wavelength squared to obtain the slopes of best fit, which actually gives us the rotation measure, and hence some indication of the magnetic field strength along the line of sight. So apart from radio sources and quasars, FRBs can also be used as cosmological lighthouses to diagnose large-scale magnetic fields in a similar way. So in fact, I would say that FRBs have an extra advantage of breaking the degeneracy between electron density and magnetic field because of their unique observable, which is the dispersion measure. So if you consider both the DM and RM, many previous works have constrained the large-scale magnetic field strength to be of the order of below tenths of nanogauss. And here, if you're interested to find out more what we can do with FRBs as cosmological probes, feel free to check out my collaborator Tetsuya's talk, which I believe is now on YouTube. So what's truly exciting here is that soon enough, we should be able to put more stringent constraints on the first magnetic fields when the world's largest radio telescope, the SKA, comes online. And the SKA is expected to carry out an all-sky survey of millions of extragalactic rotation measures, which is many, many times of what we can see now. And for comparison, on the left is our Faraday sky in 2012 with about 40,000 sources, whereas on the right is the latest Faraday sky map, which came out early this year with over 55,000 sources. And what we can see here is that the large-scale features of the field remains largely unchanged between the two maps, but the small-scale information related to the magnetic field of the Milky Way has greatly improved with a higher density of rotation measures. So we can imagine that with more extragalactic background lighthouses being detected and being localized, such as FRBs, the SKA would have a huge impact on cosmic magnetism science. So it is timely and very important for us to gain a better understanding of the rotation measure method and how it is related to the magnetic field strength along the line of sight. So this equation is widely used and it is derived from the theory of polarized radiative transfer, assuming that there's no absorption, no emission, no Faraday conversion, and that only thermal electrons are present. And it is often argued that the correlations in the observed rotation measure fluctuations tell us about the length scales on which the magnetic fields vary. Now, the conventional approach is to model the rotation measure fluctuations as some kind of random walk process. So as such, the standard deviation of the rotation measure actually quantifies the fluctuations in the line of sight magnetic field. And most studies on cosmic magnetism actually use this expression I'm showing here. So the big question is the equation really valid in all astrophysical scenarios? When is it justified to be used? And when does it deserve caution? So to address this question, I carried out Monte Carlo simulations to compute the rotation measure fluctuations. First using the conventional approach I showed earlier, and then I compare it with the results from a standard polarized radiative transfer calculation. And here is one of the key results from the conventional approach. So let's do an eye test remotely, everyone, and see if you can spot any difference between each panel that I'm showing here. Do you see any difference at all? Well, the answer is no. They all pretty much look the same. And there's nothing wrong with our eyes. But what if I tell you that these are actually rotation measure maps that are generated using completely different distributions of density and magnetic fields? So in fact, what you're seeing here in the top panel are generated from densities and magnetic field strengths, which have a Gaussian distribution, whereas the ones in the bottom have uniform distribution for the densities and magnetic field strengths. And furthermore, for the ones in the bottom, I deliberately made the magnetic fields unphysical and non-divergence free. So what this shows us is that from just by looking at the rotation measure maps alone, it is not a trivial task to characterize the electron number densities and the magnetic field strengths. Now, not only that, we also found that the conventional approach is unable to distinguish between various distinct distributions of densities and magnetic field strengths. So what I'm showing here in the red dotted box is that the conventional approach cannot actually tell apart whether the distributions of densities are uniform, Gaussian, fractal, or log normal. And it's the same case for magnetic fields as well. Apart from that, the conventional method also do not work for distributions with fractal and log normal density distributions. Now, this is actually quite a problem because fractal and log normal density distributions are actually quite common in many astrophysical systems, such as the ICM and molecular clouds. And in the last couple of minutes that I have, I wish to highlight several subtleties that we should be aware of if we want to quantify rotation measure fluctuations correctly. So first of all, the fluctuations of density and magnetic field strengths along the line of sight and across the sky plane can be different. So what I'm showing here is an illustration. So what we see here on the sky are two similar angles. However, each one of them has a different characteristic length scale along each line of sight, A, which has two length scales, and B, which only has one. Now, what's interesting is that each of these length scale do not actually correspond to the length scale that we see on the sky. So what this means is that when we take a radio picture of the sky and derive a correlation length scale of the magnetic field, this does not necessarily translate directly to the correlation length scale of the magnetic fields as they evolve from the past to the present. And another point to take note of is the possible contamination in the power spectrum that we measure. So in reality, the power spectrum of the observed polarization may be contaminated by emissions from the intervening medium and the embedded sources along the line of sight. So for example, we carry out a radio observation of the sky at a fixed frequency. So observationally, the power spectrum we measure is the result of the contributions from sources at different redshifts, and we pick up different components at higher wave number K. On the other hand, theoretically, a snapshot of a cosmological simulation only allows us to pick up all the sources at a single redshift. So it does not contain any contribution from the higher redshifts. And hence, when we see, for example, a higher power in the smaller scales in our power spectrum, for example, it may not be truly from the magnetic field itself. It could be due to, for example, emissions from the medium and embedded sources at different redshifts.
About 2 minutes, Alvina.
Oh, thank you. Right, so in the last 2 minutes, in summary, the key take-home message from here is that to please be very careful when we try to interpret magnetic field properties from rotation measures. And I would strongly suggest a polarized radiative transfer calculation as a more robust alternative. So if you're interested in more details, please take a look at these two papers here, or feel free to ask me any questions after this or in Slack if you're catching up on YouTube. So that's all from me today. Thank you very much.
I'm
Thank
clapping
you,
on.
Jason.
I'm clapping on behalf of all the other participants.
Mm.
Thank you very much, Alvina, for that very thought-provoking talk. While we're waiting for questions to appear in the Q&A, maybe I'll make one comment kind of related to some of the things that you're saying. I think it's also important that we as a community quantify how Faraday thin the FRB signals we detect are. I think in the context of a lot of FRB models, you would expect the signal to be completely Faraday thin in the sense that it's just completely behind the Faraday screen. But I would imagine that in some of the models, like the shock models, that it might be possible to see a range of rotation measures from a particular source, a small range, not be completely Faraday thin. I don't think that would strongly affect what you're talking about in terms of measuring the IGM. And then another comment would be also that, especially at low frequencies, to be a bit more focused on also making sure that we correct for the ionosphere as well, because that can also have subtle effects that can affect how we interpret small variations, especially from repeaters. So
Yes.
let's see. Do we have any questions? Oh, okay. We do have a question from Sriharsh Tendulkar. Alvina, great talk. Can you comment on the observational aspects? What should observers aim for that would provide usable and interpretable metrics? Yeah, so basically, how can we as observers be better in reporting polarimetric information and RM measurements, Alvina?
So I would say that it would be best to keep the Stokes measurements. So as far as I know, because I'm a theorist, but I think observationally for radio astronomers, what we measure are the Stokes parameters, the IQ/UV. And what happens usually is that by convention, we tend to just translate that to rotation measures and then use that as representation. But like I said in my talk, rotation measure works only in certain circumstances, in limited sort of physical conditions, like when you have, say, only thermal electrons present, or when you have no absorption or no emission in the medium. But in reality, that's not the case, right? We could have extreme circumstances like what you mentioned earlier, Jason, like this sort of different effects, or if it's in an extreme environment, then we have to do a better job. And to do that, I think if we keep the IQ/UV and from there we do a polarized radiative transfer as a comparison, I think that would keep more information and would lose less, rather than just sticking to rotation measures.
Yeah, for sure. Yeah, I agree. We have time for one more question, I think, if there are any. Alvina, I think you're on the Slack, so if people have questions, then they can ask you there as well in the dedicated channel for this session. If not, thanks again.
Thank you. I'll release my screen.
Thank you very much. And that will give me the opportunity to hand things over to the IT department to share the next talk, which is a pre-recorded talk, but I think Stella will be online in the B version of this session to give the talk live. So the next talk will be by Stella Ocker from Cornell University, and she'll be talking about leveraging the combined scattering and DM budget of FRBs. There we go.
Okay, hi everyone. I am Stella Ocker, and I am a fourth-year PhD student at Cornell working with Jim Cordes and Shami Chatterjee. And today I will be talking about leveraging the combined DM and scattering budget. So FRBs are generally extragalactic and propagate through a wide range of media along their journey to the observer, as illustrated in this diagram. And I'm going to focus on how a joint assessment of FRB dispersion and scattering can be used to probe turbulence and ionized gas along their journey. And so in particular, turbulent density fluctuations follow a power law wave number spectrum given by this equation, where Cn squared is the amplitude of the turbulence wave number spectrum, and beta equals 11/3 for Kolmogorov turbulence, and the spectrum extends from an outer scale wave number QO to an inner scale QI. I'm going to focus on how we can constrain turbulent fluctuations both in our own Milky Way disk and halo, and also the halos of other galaxies. But I'm also going to talk briefly about how scattering can actually be used to assess the plausibility of host galaxy associations, and how scattering can be used to improve estimates of DM contributions from host galaxies and the corresponding redshift estimators. So there are three main scattering observables: pulse broadening, scintillation bandwidth, and angular broadening. This diagram in the middle shows a ray tracing simulation, with the black lines showing arbitrary rays launched from a source at S through a homogeneous medium to an observer at O. And these colored lines show all of the rays that actually reach the observer. So you can see that the rays with the largest angles of arrival correspond to the longest ray paths and the longest time delays. On the left, we have a diagram showing the kind of typical two-screen scattering geometry that we believe may be relevant for many FRBs. Now, the relationship between pulse broadening and dispersion measure DM can be very simply quantified using the fluctuation parameter. So the pulse broadening time is given by this equation here, where nu is the observing frequency, g-scat is a geometric leverage factor that I'll talk about more in a few moments, DM is dispersion measure, and the fluctuation parameter is this F tilde. So F tilde arises in the ionized cloudlet model from the statistics of density fluctuations in the ionized cloudlets. So it's related to zeta and epsilon squared, which describe the density fluctuation variance and variations in the mean density. And it's also related to the volume filling factor of the gas F and the outer and inner spatial scales of the turbulence spectrum, LO and LI. So on the left, we have a very simplistic cartoon of what this ionized cloudlet model looks like. And I'll note that pulse broadening is also related to the other scattering observables. In particular, it's related to the scintillation bandwidth through the uncertainty principle, and the scintillation bandwidth can be related to the angular broadening through the distance to the scattering screen, assuming a single screen scattering geometry. Now, when we talk about scattering on an extragalactic screen or lens, we also have to apply a redshift correction that accounts for time dilation. Now, you can see from this simple relationship between pulse broadening time and DM that constructing a scattering budget inherently involves the DM budget, the fluctuation parameter, which varies between different line of sight components, and finally, the geometric configuration of the source lens and observer that's quantified by g-scat. So g-scat is given by this equation where these relative distances are between the source lens, the lens and observer, and the source and observer, and this L refers to the path length through the lens. Now, this plot on the right shows the behavior of this geometric factor versus the ratio of lens to source redshifts, and these different curves correspond to different values of the source redshift. So you can see that generally speaking, this geometric configuration will amplify scattering the most for a lens about halfway between the source and observer, but the amount of amplification that you receive from this geometric configuration also can be modified by the F tilde fluctuation parameter and DM contributions of the lens. Now, I think it's easiest to calibrate our physical intuition for the fluctuation parameter to the Milky Way disk. So in this plot, I'm showing you the distribution of pulse broadening time divided by DM squared versus galactic latitude for all pulsars with scattering measurements. And on the right-hand axis, we have the corresponding values for F tilde. So this blue band is showing the mean value of the fluctuation parameter for galactic latitudes above 20 degrees, which are dominated by the diffuse thick disk. And the mean value we find is about 0.003, with these funny units because of the fluctuation parameter's dependence on the outer and inner scales of the turbulence spectrum. We also find that the maximum amount of pulse broadening from the thick disk will be on the order of tens to hundreds of nanoseconds at 1 gigahertz, very small. Now, you'll also notice that as you move towards the galactic plane at low latitudes, and also towards the inner galaxy, which is highlighted by points in orange, you see this orders of magnitude increase in the fluctuation parameter, which directly corresponds to the different physical structure of the ISM in this region of the galaxy. So in the thick disk, we have the very diffuse warm ionized medium. Because of the dominance of FRB lines of sight at these latitudes, given our current observational coverage, the thick disk is relevant for many FRBs, but as you move into the galactic plane, you start to sample the spiral arms, more H2 regions, supernova remnants. Basically, the number of inhomogeneities in the ISM increases dramatically, and you see much enhanced scattering as you move into the galactic plane, and in particular towards the galactic center. Now, this behavior of the fluctuation parameter between different regions of the galaxy is actually one of the main reasons why the galactic tau-dm relation for pulsars does not directly apply to extragalactic sources like FRBs. And if you're particularly interested in learning more about how the fluctuation parameter ties into the galactic tau-dm relation and the implications, please feel free to ask me afterwards. So we can use this relationship between pulse broadening time and dm to actually constrain the fluctuation parameters of galaxy halos. And the way that we do this is first by focusing on the Milky Way halo. And to give away the punchline, I'll say that our analysis actually indicates that scattering from galaxy halos is negligible for the lines of sight that we consider. So we approximate the amount of scattering that's contributed from the galactic halo as being less than or equal to the total amount of scattering that's observed. This we constrain using two well-characterized lines of sight, FRBs 121102 and 180916. And we subtract the amount of scattering that comes from the Milky Way disk using NE 2001. Now, our likelihood analysis of the FRB scattering times gives us an upper limit on the product of the fluctuation parameter and dm squared for the galactic halo. And then we can apply a given model for the dm contribution of the galactic halo to get an upper limit on the fluctuation parameter. Now, we actually perform a very similar analysis for two other FRBs that have been associated with galaxy halos intervening their lines of sight, and those are FRBs 181112 and 191108. Now, before I show you our final results on the fluctuation parameter for these various halos, I'd like to give a brief example of how the scattering budget works for 121102. So because 121102 has both a scintillation bandwidth and an angular broadening, we can place a constraint on the distance to the dominant scattering screen along this line of sight. This plot on the left shows the measured angular broadening in blue and the angular broadening implied by the scintillation bandwidth in green. And the overlap of these two curves gives the distance to the dominant scattering screen, which we find is about 2 kiloparsecs, consistent with the distance to the outer spiral arm. On the right, we have the dm, density, and CN squared predicted by NE 2001 along this line of sight, and we find very good correspondence between NE 2001 scattering prediction for this line of sight and the observed scattering measurements. So, in short, the scattering for this line of sight can be explained by the outer spiral arm, and very little scattering is allowed from the Milky Way halo. Now, jumping ahead, these are our final constraints on the values of the fluctuation parameter for 3 different galaxy halos and for various regions of the Milky Way. Here we have on top M33, which is in the foreground of FRB 191108. FG 181112 is in the foreground of FRB 181112, and then the Milky Way halo we constrain using 2 FRBs, 121102 and 180916. Now, we also show various values for different regions of the Milky Way and for the Large Magellanic Cloud, which is constrained by BO 540 minus 69. So BO 540 lies inside a supernova remnant and has enhanced scattering, giving rise to a very large fluctuation parameter, comparable to values in the inner galaxy. Now, the main thing to note is that the values for the fluctuation parameters for these 3 halos are very small and correspond to small to negligible amounts of scattering from these halos. So on the right-hand side, we have the amount of scattering at 1 gigahertz that we constrain for these different regions. Now, I'll briefly note that the fluctuation parameter could be a promising diagnostic for multi-phase models of the circumgalactic medium. In particular, we expect that the fluctuation parameter will be much larger in the warm ionized medium than in the hot ionized medium because the filling factor and outer and inner scales of turbulence are much smaller in the warm ionized medium than in the hot ionized medium. And our analysis initially suggests that the galaxy halos we consider contribute negligibly to scattering for a few well-characterized lines of sight, which may favor the hot ionized medium. And further analysis will hopefully let us distinguish between models where the CGM includes cool, clumpy gas. Now, I want to briefly mention how scattering can actually be used to bolster host-galaxy association, so switching gears now. And I'm going to do this using FRB 190520. So you heard Reshma's great talk about the polarization of this FRB, and Dee Lee will be giving a much better description of the discovery of this FRB in the late breaking news talk. But to briefly recap, this FRB was localized to a dwarf galaxy at a redshift of 0.24, and the implied host galaxy DM is about 1100 parsecs per cubic centimeter in the host frame, extraordinarily large. And one possibility that we considered was that what if the observed galaxy is actually a foreground galaxy intervening the line of sight to a background FRB source? And what we determined is that the observed scattering time is actually far too small to allow this possibility. So in particular, this comes down to the behavior of the geometric leverage factor G-scat for these different line of sight configurations. So for scattering in the host galaxy, G-scat will be about 1, but for scattering in the intervening galaxy, it will be orders of magnitude larger. So this plot on the right is showing G-scat versus host redshift for a fixed lens redshift of 0.24. And these three curves correspond to different values of the path length through the lens. And so you can see that as you move the FRB host behind the observed galaxy, you would expect an orders of magnitude increase in G-scat and in the observed scattering. And so the scattering time that we observe, about 10 milliseconds at 1.3 gigahertz, is actually far too small to allow the observed galaxy to be an intervening galaxy. So bottom line, we have affirmed that the observed dwarf galaxy is indeed the host galaxy of this FRB, and this leaves us with the continually intriguing puzzle of how this galaxy contributes such an extraordinarily large DM. Now, I'm going to wrap up this presentation by describing some recent work that's being led by Jim Cordes, and which is actually an analysis demonstrating how scattering can actually bolster host galaxy DM contribution estimates and corresponding redshift estimators. So the basic picture is that if we can constrain the host galaxy scattering contribution, that actually can be converted into a DM estimate for the host based on plausible ranges for the fluctuation parameter. And that in turn serves as input to the DM budget, which constrains the host redshift. So we've constructed a Bayesian analysis that essentially connects FRB DM and scattering budgets with redshifts in order to construct probability density functions of the DM from host galaxies for all currently localized FRBs. One example of this is shown on the right for FRB 190523. In the top panel, we have the DM contribution of the host, and on the bottom, the scattering time contribution, and this is versus host galaxy redshift. So this red line corresponds to the measured redshift, and the green line to the observed scattering. And so one of the main things to take away is that as you move the host galaxy redshift up, you essentially quench the amount of scattering that is allowed from the host galaxy. And when you make the host galaxy redshift too small, then the amount of scattering that's implied will be too large to explain the observed scattering. So in essence, the scattering you observe corresponds directly to a limit on the host galaxy redshift. And we also demonstrate that you can use the same formalism to test potential host galaxy associations. And we've also demonstrated that for unlocalized FRBs, scattering can actually improve redshift estimates. So for more on that, I highly encourage you to check out this paper, which will be posted on the archive shortly. Now, we also show in this work that the scattering-based redshift estimator also serves as a test of the cosmic baryon fraction. And so my timer went off, so I'm going to go through this very briefly. The basic idea is that for values of the cosmic baryon fraction that are too large, you would get an implied DM contribution from the IGM that would dominate the DM budget. And so you wouldn't have enough scattering allowed from the host galaxy to explain your observed scattering. And if you make FIGM too small, then subsequently you would get a DM contribution from the host galaxy that's far too large to explain the host scattering contribution. And so on this right-hand side, we're showing the redshift, the RMS residuals between the estimated and observed redshifts for 9 localized FRBs as a function of FIGM. And so this blue curve corresponds to the DM-only redshift estimator, and the green and red curves correspond to the DM and scattering-based redshift estimator. And so you can see that the RMS residuals for the scattering-based redshift estimator actually turn up after a value of about 0.9 for FIGM. And we find that values of around 0.8 for FIGM are favored, consistent with previous studies. So I'm going to very quickly wrap up by leaving you with this conclusion slide and mentioning that in future, we still have work to do in terms of characterizing the frequency time structure of FRBs, and that is absolutely critical to actually using scattering for these powerful applications. And we still have a lot to learn about FRB host galaxies, which will potentially yield some really exciting new information about FRBs and their progenitors. So with that, I will happily take any questions.
Wow, that was great. Stella, I'm clapping on behalf of everyone, even though you're not here right now. So we have a couple questions. Are there any? Please raise your hand if you are a collaborator who could answer any of these questions. If not, I'll just read them out and then we'll place them in the Slack channel. So Ryan Shannon is asking, is the observed scatter broadening in FRB 190520 consistent with the putative host DM? That's a good question. I'll post that in Slack, Ryan. And Lucy Oswald is asking, saying, really nice talk. I was wondering, what method do you use to measure the scattering times of the FRBs? Also a very good question. I think in some cases it's based on scintillation bandwidth, and sometimes it's in the time domain, but I'm sure Stella has some comments on that as well. Okay, great. So unless there are other questions or comments, we'll move on to the next talk, which again will be a live talk. So Ryuichi, would you like to share your screen, please?
Yes.
Our next speaker in the session is Ryuichi Takahashi, who's going to be talking about statistical modeling of the cosmological dispersion measure. I'll let you know when you have 3 minutes left, Ryuichi.
Oh, okay. Thank you for giving me a chance of the talk. My name is Ryuichi Takahashi, and I'm working on this project in collaboration with Ocker-san. And this talk is based on a paper published in NRAS. So if you are interested in my talk, please check this paper later. And in this talk, DM stands for the cosmological dispersion measure, including ionized gas, comes from ionized gas in IGM and intervening galaxies. And in this talk, we don't consider the Milky Way contribution or host galaxy contribution. And previously, there are 2 theoretical approaches for the DM statistics: analytical approach and numerical simulation approach. And the analytical approach commonly uses based on the Halo model. And the other approach is numerical simulation approach. It uses cosmological hydrodynamic simulations. And our approach is, how can I say, hybrid of these approaches. So we made analytical model calibrated with the latest cosmological simulations. And the main purpose of our study is, the first purpose is we model the 2-point statistics of dispersion measure using the hydrodynamic simulations, latest hydrodynamic simulations, Illustris TNG 300. We first measure the free electron abundance and power spectrum of its spatial fluctuations, because you know, the DM statistics are fully determined by the free electron statistics. The DM statistics are just a projection of the free electron statistics. And we then provide analytical model of the DM statistics using fitting functions of the free electron distribution. And next, we then validate our analytical model against mock DM measurements. And let me briefly mention Illustris TNG 300. In the previous session, Fei Wong already mentioned, I think, this simulation. This is the state-of-the-art hydrodynamic simulations, and the simulations follow gravitational evolution and astrophysical processes, including star formation, gas cooling, and stellar and AGN feedback. And the simulations reproduce free electron distribution in the universe. And there are 3 different resolutions named TNG 301 to 303. And 301 has the highest resolution. And that and TNG team also released a dark matter only simulation named TNG 301 dark. And this dark matter only simulation can be used for studying the difference between the free electron distribution and dark matter distribution in the universe. And this is the result. This figure plots the free electron fraction measured from the TNG simulations. The vertical axis is free electron fraction as a function of redshift. And free electron fraction is defined as number of free electrons over total number of electrons. So total number means, let's say, free electrons and electrons bound in atoms. And the colored symbols are the results measured from TNG simulations. And according to the simulations, the current free electron fraction is about 95%. And the red curve is our fitting curve. And this figure shows the power spectrum of the cosmological free electron distribution. And this is, how can I say, one of our main results. And the vertical axis is power spectrum as a function of wave number k. And the colored symbols are the result measured from the simulations. And the gray open symbols are dark matter power spectrum measured from dark matter only simulation. And the bottom panel plots the bias factor. Here, bias is defined as the free electron power spectrum divided by the dark matter power spectrum. And the red curve is our fitting curve. And you can see at large scales free electrons exactly trace the underlying dark matter. But at small scales, free electron fluctuations are strongly damped due to stellar and AGN feedbacks. So in the bottom panel, the bias factor is unity at largest scales, but at small scale, it is damped, strongly damped. And our analytical model uses these fitting functions, this fitting curve and previous this fitting curve for free electron abundance and power spectrum. We also made mock sky maps of DM based on a standard ray tracing technique. And here it's an observer, and we placed simulation boxes along line of sight, and field of view is 6 by 6 degrees squared. And we calculated free electron column density along the straight ray path. And this is an example of the contour map at source redshift 1, but I skip this one. And this figure shows the mean and the 1 sigma scatter of dispersion measure. And the vertical axis is DM divided by source redshift, and x-axis is the source redshift. And these colored symbols are simulation results, mean with 1 sigma standard deviation. And solid and dashed curves are based on our prediction of our analytical model. Mean and plus minus 1 sigma deviation. And you can see our analytical model agrees well with the simulation results. And this figure is the probability distribution of DM for source redshift unity, but I skip this one. And this figure is probability distribution of source redshift for a given DM dispersion measure. The probability distribution as a function of source redshift. And here, the dispersion measure is fixed by 1000. And the colored histogram are the simulation results. And it's how can I say, the scatter in source redshift is about 20%. And you can see the simulation results are well fitted by a Gaussian distribution denoted by the red curve. Finally, we also compute angular 2-point correlation function of dispersion measure. It's a correlation function between the dispersion measures at different sky positions at theta 1 and theta 2. And here, the theta is angular separation between them. And then the angular cross correlation is defined by this equation. It is a standard definition, I think. And our analytical model predicts this correlation can be described by the simple expression. The cross correlation is simply proportional to the inverse of theta for large angular scales larger than 1 degree, and source redshift is larger than 0.3. And we expect this correlation function will be detected using thousands of FRBs in the near future. And this figure plots angular cross correlation function for ideal full sky observation measurement angular cross correlation as a function of angular separation theta. And in the vertical axis is correlation function times angular separation theta. And the red curve is our analytical prediction. And shade regions are 1 sigma error regions determined by survey area and shot noise here. And in this plot, we assume host galaxy, the dispersion measure scattered by host galaxies are 50.
About 3 minutes, Ryuichi.
Okay, thanks. And orange dashed line is our simple power of it, and this one. And these different shaded regions correspond to different number density of host galaxies. For example, the lightest shaded region corresponds to 0.1 host galaxies per degree squared, and the darkest shaded region corresponds to 10 host galaxies per degree squared. And these error bars are at large scales. The error regions are mainly determined by the cosmic variance. And we also make our numerical code publicly available. And our numerical code computes free electron statistics, for example, abundance and power spectrum, and also DM statistics, mean, variance, angular power spectrum, and angular cross correlation function based on TNG simulations. So if you are interested in our code, please visit our archive page and click here. This is our conclusion. Yes, that's all. Thank you.
Thank you very much, Ryuichi. Very interesting. We have time for questions. If you have any questions, please post them in the Q&A here. We can also post them in Slack. All right, we have a question that's popped up. This one is from Robert Lillo, who says, in the Bahamas, all capital letters simulations, gas was found to be biased even on large scales. And then Robert provides a reference. I naively would expect the electrons to behave similarly. Could you comment on that difference to the TNG 300 result?
Yeah, but just a moment, please. So I think it is referring to this plot, I think. But in my opinion, according to the perturbation theory, at the largest scale, I think the free electron should, how to say, distribute proportional to the dark matter distribution. So I think at the largest scale, the bias should be unity, in my opinion. But yeah.
Do you have any further comments, Robert? You can unmute if you want to clarify your question.
Yeah, sure. No, I see the point of the perturbation theory. I'm not perfectly sure if it holds. I mean, I've read your paper, so I've seen the point. It seems like in the Bahamas simulations, they didn't do the assumption and just, well, check what they got from whatever the feedback model does into those scales. So I'm still not perfectly sure what is really happening there, but maybe, I don't know if you have to say something more, or maybe we can also discuss at a later point.
Okay, yeah. Any reactions, Ryuichi? I mean, yeah, you guys should continue to discuss on Slack or in GatherTown.
Yes. Yeah. We will discuss later in Slack.
Okay, let's do that. Thanks.
Okay, sounds good. We still have time for another question or two, if there are any. Something new has popped up in the Q&A. Vivek Gupta asks, your model predicts a constant angular spectrum coefficient in the range 0.3 to 1.0. Z is between 0.3 and 1.0. What redshift do you expect the angular power spectrum of FRB-DM to start showing evolution? At what redshift?
Yes, our model predicts constant angular power spectrum at source redshift over 0.3. So we don't have such an upper bound. This is because, how can I say, at largest scales here, largest scales, how to say, the nearby structures mainly contribute to the angular power spectrum, angular correlation function. So how can I say, how to say, distant structures, for example, redshift 1 or redshift 2, does not contribute to such large scale signal, I think. So is it an answer to you?
We can ask Vivek 1 sec. Let me just unmute him. Vivek, does that answer your question?
Yeah, that does answer the question. I'll think about more if that if I have any further follow-up, but thanks for the answer, Life.
Okay, great. Do we have any other questions for Ryuichi? Okay, if not, then thanks again, Ryuichi.
Thank you.
And I'm sure people will contact you offline to discuss further. We will move on to the next talk, which is the other recorded talk in this session. This talk will be given by Dana Simard and from Caltech. And let me just look up the title before I start the video. I'm realizing the error of my ways in terms of the number of tabs I have open right now. Dana will be talking about turbulence in extragalactic ISM illuminated, turbulence in extragalactic interstellar medium illuminated by fast radio bursts. So I will start the talk now.
Hi everyone, I'm Dana Simard and I'm a postdoc at Caltech. And today I'm going to talk about studying turbulence in other galaxies using fast radio burst scattering. And this is work that I've recently submitted to the archive, and you can check out the link here. So I'll start by discussing what we know about turbulence in the Milky Way. So in the Milky Way, we have this advantage of having many different tracers of both velocity and density fluctuations over a very large range of scales. And so the figure here shows the power spectrum density over scales. If you look at the x-axis here, we're looking at scales between 10 to the 7 meters and 10 to the 18 meters, so more than 10 orders of magnitude. And at the very large scales here, we're looking at velocity fluctuations in the ISM, whereas at very small scales, we're using scattering of sources like pulsars and AGN, and including VLBI observations of AGN. You can see that this remarkable result that over these more than 10 orders of magnitude, these tracers all fall along this very simple power law, which is characterized by a single power law index, beta, between the cutoff on small scales, which is the inner scale where energy is dissipated, and the outer scale on large scales where energy is injected into this turbulent cascade. And this has been coined as the power law in the sky by Armstrong, Rickett, and Spangler in their classic 1995 paper. This spectral index that we see in the Milky Way is consistent with what we expect for Kolmogorov scattering, which is an isotropic turbulent spectrum between the outer and inner scale. And even though we have all of these tracers and all of these ways to study turbulence in the Milky Way ISM, some questions still remain. So in particular, we see extreme scattering events towards pulsars and AGN, and this suggests that perhaps these sources and scattering of these sources is actually not probing the same spectrum as what we're seeing at other scales. And so maybe the sources that we're using to study very small scales are actually misleading us. But when we get to other galaxies, we have even fewer tracers. We have very few tracers to work with. So we can still access the velocity information, even if we don't have a nice velocity map of the host galaxy. We can look at the line widths of emission lines in the host galaxy, provided we have some understanding and some model for contributions to the line width from bulk motions of the gas or from thermal motions of the gas. We can then extract the non-thermal contribution to the line width, which tells us about the velocity fluctuations at the outer scale. We don't have access to pulsars simply because they're not luminous enough, but luckily fast radio bursts undergo scattering like pulsars do in the ISM of their host galaxies. And this is characterized by tau, the characteristic scattering time, which is used to define the exponential scattering tail. And this is proportional to the scattering measure, which is how we typically talk about the scattering properties of the actual plasma, and is proportional to that density fluctuation amplitude Cn squared. And in this case, we're looking at scales below the Fresnel scale, which is about 10 to the 8 meters for scattering in the host galaxies, which is what I'll focus on today. So in order to relate these two tracers in other galaxies between these very different scales, we need to do two things. We need to relate the power in turbulent fluctuations on these different scales, which we've talked about a little bit by looking at that power law in the sky in the Milky Way. And so we can make some assumptions that it follows the same relative spectrum as in the Milky Way, maybe with a slightly different power law index or a different amplitude in the fluctuations. We also need to be able to relate the velocity and the density fluctuations. And this depends on properties of the gas, including things like the sound speed and the average electron density in the medium, as well as some details on how turbulence is driven in the medium, which is parameterized by this value B, which we're going to take to be about 1. So I'm going to present a case study. In this case, I am looking at a specific fast radio burst that is associated with an H alpha region in its host galaxy. This is what I kind of started with this work, because then we have a specific region that is emitting that is close to the fast radio burst and has a defined scale that we can assume is the outer scale, and have well-known properties like the temperature and sound speed in the gas. And so we're going to use H alpha or H beta line widths from the associated region to determine the non-thermal velocity dispersion and the fluctuations that are contributed by turbulent velocity in the gas. And then from fast radio bursts, I'm going to use the extragalactic scattering measurements, but you can also use constraints, and assume that this arises in this H alpha region so that we can relate the scattering measure to the non-thermal width that we see, and the non-thermal velocity dispersion. And so we are making an assumption about where the scattering is occurring, and that it is occurring in the host galaxy. And I'm going to use the same power law as in the Milky Way, and an outer scale of about 150 parsecs and an inner scale of about 1,000 kilometers. So today I only have time to really focus on one of these case studies. But okay, before I get into that, quickly, so if we see some inconsistencies between the scattering measures that we get from from the FRB observations, the radio observations, and the line widths from optical follow-up of the host galaxy, then that tells us that one of these assumptions is wrong. So this could be that the form that we have of the power spectrum is incorrect. So maybe there is a slightly shallower, slightly steeper index. Maybe there is a break in the power spectrum or increased power at some scales. It could mean that that different structures are contributing to the two tracers that we have. So for example, if we have something that is small, like a supernova remnant that's contributing to scattering of the fast radio burst, then we likely won't see the influence of that on large scales that are probed by the velocity dispersion at the outer scale. So this is basically an increase in power on smaller scales, and it would cause this mismatch between our two tracers with our assumed power law, simple power law form. Or if we see more scattering from the velocity width than what we get from if we see more power and fluctuations from the emission line width than from FRB scattering, then that tells us that the FRB must not be going through that plasma, or that's a possibility. So we have these kind of variety of cases that could be causing this discrepancy. And so if we can narrow down the difference between these cases, then we can use FRB scattering combined with other tracers of turbulence in the host galaxy to both understand the local environment of the FRB source, as well as to understand turbulence in these galaxies. So the one case study that I'll be able to talk about today is FRB2021 0608b. This was a fast radio burst that was localized by ASCAP to a specific knot of star formation in the spiral arm of its host galaxy. And it has a measured extragalactic scattering timescale of about 3.3 milliseconds, measured by Shuri Day and collaborators. And this temporal scattering is unlikely to arise in the foreground. So Sunil Simha and collaborators did a very detailed study of the foreground galaxies, which included predicting where missing, so galaxies that were not sensitive to or filamentary structure in the IGM would reside, and found that even taking this into account, it's very unlikely that the scattering is coming from the foreground. And so it is most likely originating in the host galaxy, even though we can't say that for sure. So using the H alpha, or sorry, in this case, H beta line width in this knot of star formation that you see here, in order to get the turbulent, the velocity power fluctuations and convert that to density power fluctuations at large scales, which is shown as this blue circle here on the left-hand side of this plot. And then comparing that to this scattering timescale, from which we get the scattering measure and the power on small scales, which is shown here on the right-hand side of the plot. You can see quite clearly that the scattering measurements indicate a much higher power on small scales than what we would extrapolate from the non-thermal velocity dispersion. And this is more than 5 orders of magnitude larger. So it's a very large discrepancy. So how can we reconcile this? What can we do to fix this, to explain this discrepancy? So one possibility is that we have the index of this power law wrong. And if we have a shallower power law index of about 3.2, then these points line up. But instead, it could also be due to excess power on small scales. And so this is something, this conundrum of 2 different explanations for this increased power on small scales compared to our expectations from a Kolmogorov turbulent spectrum is something that is seen towards the Milky Way galactic center. And again, there's this question of whether there's increased power on small scales or due to a bump in the power spectrum or due to a shallower power spectrum. And so to distinguish between these two cases, what we really need are additional tracers. So we have a few options for finding additional tracers of our power spectrum. One is to look at intermediate tracers. So if you recall from that power law in the sky plot, in the Milky Way, we use dispersion measure variations or looking at fringe tilts in the dynamic spectra of pulsars in order to constrain fluctuations on intermediate scales. And both of these are quite challenging for fast radio bursts, and even in cases where they can be achieved, they can only be applied to repeaters. And so they're not applicable to one-off events. But we could also look at constraining the slope on either end of this power spectrum. And on small scales, one way to do this is to look at the frequency evolution of scattering. And Cherie Day and collaborators actually do this for this source in 1906-08b and find a power law spectrum that's consistent with either a Kolmogorov turbulent spectrum or with the shallow slope that we infer from these 2 points on our power spectrum plot. On large scales, there is the possibility of actually modeling resolved emission lines in order to extract the velocity power spectrum. This is something that's been applied to the Milky Way, but has not been attempted for both ionized lines, so H alpha or H beta compared to neutral lines that have a much smaller thermal contribution, and hasn't been applied to galaxies except for the Milky Way and I think the LMC. Yeah, so I will finish up here with a final slide. So I hope I've showed that there is a promise for using fast radio bursts to understand the properties of turbulence in other galaxies on very small scales, and for comparing this to other tracers to understand turbulence over a range of scales in these galaxies. And that this holds promise also for understanding the local environments of fast radio bursts, as well as understanding turbulence in galaxies other than the Milky Way. I didn't have a chance to go into it today, but we expect that future surveys will be able to detect fast radio bursts where we can actually confidently attribute scattering to the host galaxies using the presence of galactic scintillation and scattering tails. I think this has been talked about a little bit during this conference, and future surveys, especially ones with very wide bandwidth, will be able to do this, and for a large number of sources. And a lot of the uncertainty that we have right now is actually in this analysis is relating and constraining the properties that are needed to relate the density and velocity fluctuations when we're combining these tracers. And so we can use additional follow-up of these galaxies in the optical to really really constrain these parameters in order to get a more accurate comparison of the velocity and density fluctuations that we're looking at in this work. And I think that's all for today. So I will take any questions on Slack. And if you have any more questions about some of these points up here that I didn't have time to really delve into, please also message me on Slack. Thank you.
Great. Thank you very much, Dana. If people have questions, please post them in the Q&A or in Slack. Do we have any questions or comments that people would like to make immediately? I think maybe one comment I would make is it's pretty amazing to see, like, you know, in the last 20 years or so, interest and sophistication in modeling you know, pulsar propagation effects in our own galaxy. Like, you know, think of the scintillation arc work that Dan Steinbring pioneered, and the scintillometry that Dana and others have been working on, that has developed enormously in the last 15 or 20 years, thanks also to recording baseband data in some cases and interferometric baseband data. And then at the same time, FRBs came along thanks to wide field instruments, and now these two things are coming together and allowing us to study the ISM and other galaxies. So that's really it's quite amazing to see how that's developed in the last couple of decades. Very exciting stuff. Are there other comments or questions that people would like to make? Dana will be speaking live in the B version of this session, and yeah, if you have any questions beforehand, please post them in Slack. I'm sure she'd be happy to answer them. Okay, then we will move to the last couple talks of the session, which will both be live. And the next talk is going to be given by Amanda Cook. Amanda, would you like to share your screen, please? Great. Sure. Yeah, that looks good. So Amanda is going to be talking about an FRB sent me a DM. Okay, very good. Measuring the Milky Way's plasma with CHIME FRB.
Yeah, hi everybody. My name is Amanda Cook, and I am a PhD candidate at the University of Toronto. I'm supervised by Brian Gainsler, Gwen Eady, and Paul Schultz, and I'm a proud member of CHIME FRB. So I'm happy to share today what we've learned about the Milky Way's plasma using our FRB sample. So we've talked a lot about DM contributions already in this session, so I'll try to keep this brief, but as a radio signal travels through ionized media, it picks up a dispersive delay that is proportional to its inverse frequency squared. And we can measure this, and luckily it's also proportional to the amount of free electrons along the path as a column path integral, column density. And so we can use this to study the properties of the free electrons. And so the DM that we measure for extragalactic bursts is a combination of how I define it for contributions. Starting at the source of the fast radio burst, it will first encounter its own DM host. This could include a disk, this could include a halo, this could include some kind of local supernova remnant, other contribution. Leaving its host galaxy, it will then travel through the intergalactic media, and this could include intervening halos, intervening galaxies. And then finally, it will reach our Milky Way and have to go through our halo and disk. And so the DM halo is an interesting contribution because the halo gas itself is too diffuse to be imaged directly. There are observables that we can use that we believe trace the gas content, like absorption lines in UV and X-ray. However, in order to get the total gas content from these observables, you need to make some model-dependent assumptions. And once you convert these various models into DM halo estimates, as done by Keating and Penn in 2020, they can span in an order of magnitude. And so this is interesting because if we had a really good measurement of DM halo, it could potentially inform galactic formation theory, because you might expect different contributions depending on how we made our halo in the first place. But I think another really interesting part of this estimate, which many of you are likely interested in, is any meaningful distance estimate that we make using fast radio burst DMs must have these foreground contributions subtracted. So we need a really precise DM halo estimate in order to do source or host galaxy associations if we don't have VLBI precision localization, as well as cosmological experiments, which we heard a lot about recently. So the premise of my project is super simple. If every fast radio burst is extragalactic, then in a given line of sight, every fast radio burst needs to pass through the halo and the disk, and hence every fast radio burst is an upper limit on the Milky Way contribution. This is to varying degrees, of course. Some will be very bad upper limits that are not very constraining, and some might happen to be on the outside of a very nearby galaxy, right in the globular cluster, and really constraining. So we have upper limits from the total contribution from the Milky Way, and then we can get lower limits on the disk contribution of the DM from galactic pulsars. So we can measure pulsar DMs. We expect pulsars to be mostly in the disk because they, because of the massive stars from which they are born, they have very short lifespans, and also pulsars which are very far away are pretty dim, and so we don't really expect to see them. And so if we subtract this upper limit and, sorry, the lower limit from the upper limit, we get a upper limit on DM halo, and it's purely observation based. And so that is what we're going for. And so let's kind of flip this picture on its side and look at the data that we have. So here are our FRBs in pulsar sample. This is DM versus sign of galactic latitude, but the absolute magnitude is taken. On the top, we have in triangles fast radio bursts detected by CHIME FRB, where I've noted which ones are repeaters and which ones are as of yet non-repeating. And then on the bottom in the stars, we have galactic sources like pulsars from the ATNF catalog. Those are shown in gray. And then all of the detected galactic sources with CHIME FRB are shown in this darker color, just to kind of show that we have some sensitivity down here. But what's really striking is that there's a pretty clear gap in what we're seeing between extragalactic fast radio bursts and our galactic sample. And I am here to claim that this is at least partly due to the halo, and let's build up on this plot a little bit more. So I think the first thing that I should share is the Milky Way disk model. So I've plotted 3 models here. The first 2, YMW16 and NE2001, aren't really a disk model. They're actually free electron density models of the entire galaxy, but we can use them to predict the maximum DM as a line of sight, and notably neither of them contain a component in their model for the halo, so it might be appropriately used. But I think most relevant is that CHIME FRB uses these models to determine which FRB candidates we save intensity data for. So they should definitely be considered. And so the spans in the YMW16 and NE2001 show this collapse over longitude. So it shows the range over each longitude, but only for lines of sight with declination greater than -10, which is where CHIME FRB is seeing, and only for lines of sight without really high emission measure, so that we don't probe local structure like H2 regions and other things that we're not super interested in. The last legitimate disk model is the Ocker et al. 2020. So the authors in this paper went about describing the scale height of the thick disk using pulsars with independent distance derivations. And so if you take this scale height, you can convert it into a estimate of the disk contribution to the DMs in any given line of sight, if you assume just a slab geometry of the thick disk. And so that is the yellow span, where here it's actually the model errors that this takes up the span. And so you can see we have some fast radio bursts that are really great probes, really low DM, but it's limited number of sites. So we want to, sight lines. And so we wanted to make a kind of a smooth argument between these to say, what could we reasonably conclude between our best lines of sight? And so one of the models that we use is just a simple cubic polynomial. However, it's a cubic boundary estimate in that we enforce 2 things. The first thing is that all of the FRB DMs must lie above this boundary curve for the galactic DM. And then the area between this curve and DM equals 0 needs to be maximized. That is, we're taking only the most conservative estimate we can that still supports this data. But obviously, this is super dependent on the model that you're putting in. So another one that maybe could even, I would argue that there's a little bit too much structure in here that to be physically motivated by the FRBs we have, but just it might be more conservative depending on your use, is the low S boundary estimate. So low S stands for locally weighted scattered plot smoothing. It's basically just a fitting method which penalizes outliers. And instead of using fast radio or the DMs directly to fit, because our outliers are actually our best points, we define the data at every sign B as the local minimum in 5-degree bins. Finally, or not really finally, but a lot of the halo models that I'll talk about assume some kind of spherical symmetry of DM halo. And so we can do this type of model using our most constraining fast radio burst, FRB2021 aka the repeater in M81, which I'll probably refer to it as because I think it rolls off the tongue a little nicer. So if you assume, again, this Ocker et al. 2020 slab geometry for DM disk, you can find the maximum total amount that you could attribute to the halo for this M81 repeater. It's 52 DM units approximately, and then we just plot this above the Ocker et al. Disk contribution as a function of latitude. And then mostly just to guide the eye, I have a constant, but I don't have to explain that at the M81 repeater. And so the results are essentially, depending on which model you choose and which galactic latitude you're looking at, data-based constraints for the Milky Way contribution to the DM that range from 80 to 151 DM units. And then halo constraints that lie between 45 and 119 DM units, again, assuming a certain model in galactic latitude. And so if you're looking at this gap and thinking, okay, that's tantalizing, but there could be other things that play here, I'm not sure if it has to be the halo, we're all with you. And I should talk a little bit about what else is likely contributing to this gap. So we've proven pretty certainly that at least the excess DM is a proxy for distance. And so when we're searching lower and lower DMs, we're also searching less and less volume. So you could imagine that we're not detecting fast radio bursts down in the gap just because of the smaller volume probed. Similarly, due to CHIME FRBs RFI mitigation strategies, we are slightly less sensitive at low DMs. And so I just did a really simple experiment estimating the ratio of the number of sources within these two volumes, accounting for CHIME FRB selection function. And I find that it's inconsistent. Our observations are inconsistent with the volume and instrument bias alone at a very conservative greater than 3 sigma. My argument was like very simply conservative, and I can come back and talk about it if people are curious, but definitely above 3 sigma. And at the 90% confidence level, you need more than 20 DM units from the halo or host to explain the observations that we're seeing. And so, wow, that's a lot of text. Don't worry, I'm not going to drag us all through that. I could not possibly do justice to all of the models that I will compare to today in the time I have, but I just wanted to give a proper legend in case people are on YouTube and want to pause and look at this. But I will say that the majority of the data that I have here, as well as the notation that I follow, is taking from Petraska and Zhang and Keating and Penn, which are great reference papers, and I would totally recommend the read. But I just kind of wanted to give a feel for how good these constraints are, or what the power they have is to differentiate between models. And so I'll kind of point out the highlights. We have known for a while, and this continues to confirm that the NFW profile is inconsistent. That is, we don't expect the halo gas to trace the dark matter. Most of the spans in this plot, in the lower plot of predicted DM halo, represent different input parameters, mostly high and low mass halos. And it seems like most of the higher mass scenarios of the halos in these models are ruled out. They seem pretty inconsistent with our observations. I see a lot of time people citing, when they're trying to estimate a halo contribution, they cite Dulag et al. At 2015, and they say 30 will attribute 30 to the halo. And I think that cosmological simulation remains quite relevant, looking at their spans as well. Finally, the Miller and Bregman 2013 paper is low, but you could still explain it away if the Milky Way halo is very clumpy, or if the DM from the M81 halo is much, much larger than the DM from our own Milky Way halo. I also have kind of a special plot for Yamasaki and Totani 2020, because they give estimates of the predicted DM halo as a function of galactic latitude and longitude, as they don't have spherical symmetry. So you can see how our galactic latitude models compare to theirs, and I think it agrees pretty well. There's some overlap, which could be concerning. However, since this should be a very strict upper limit, a very conservative upper limit, but again, they have to integrate over longitude, which we don't. And so at the M81 repeater spot, they're only predicting a DM halo of just over 30 as well. So it does seem roughly consistent. And the Yamasaki and Totani 2020 also helps me talk a little bit about the model uncertainties that we're facing here. So I haven't had any error bars on here yet, and it's because it's a little bit of a complicated picture. So obviously we should examine how legitimate it is to collapse over galactic longitude. If you look, so they looked at the scatter and the X-ray emission measure data, and they find that it implies for the Milky Way halo DM a fluctuation of 0.2 dex over the whole sky. And so that's what this looks like on our model. Obviously, for any fit that you run, there's some fit errors. So we can do a bootstrap to find a 90% confidence interval pointwise for this fit. And I think the one that's like the most glaring is that to this point, I've been very careful about not making any assumptions about what the host or the IGM contribution might be. But these things, especially for the most nearby repeaters, are often very well established. And you can make just a basic assumption about things being Milky Way-like and using the Makar relation to give an estimate of the isolated DM halo. So Mohit has a really great paper describing exactly what you expect this estimate to be in his M81 repeater discovery paper. But this is kind of where you might expect, how much lower you might expect it to be just in that one case. And so the true answer is likely a combination of all of these effects. And this part is a little bit of a work in progress. We're hoping to have this completed quite soon to share with the community. And so I guess that brings me to my conclusions. I'm maybe a little bit fast, but we present FRB derived constraints as a function of galactic latitude for the plasma in the galaxy and the Milky Way halo. These observation-based high latitude constraints for the Milky Way as a function of galactic latitude are between 80 and 151 parsecs per cubic centimeter, depending on which model you're choosing, whatever makes the most sense for your given case. And then subtracting the Ocker et al. Estimate for the DM disk, we can get DM halo isolated between less than 45 and 119 DM units. The future work is, well, we're trying to complete this paper right away, including the curve formulae and the full interpretation very soon, and you can see all of the models in their full glory. But then also, I guess, longer down the road, we're going to do a comparison of the longitudinal behavior and a 2D map. I kind of expect this in about 2 years at our current detection rate. We'll be able to make a distributional argument, as well as a good majority of the sky will be pretty well resolved. But I think that there's lots of potential surprises given by the universe. So we'll see what it gives us. If we have a lot more M81 repeaters, I think that this could come sooner, or if we suddenly have a better idea of a large fraction of the fast radio burst coming from a particular host, then maybe that would help us. Yeah, so thank you for the organizers for letting me speak, and I'm happy to take any questions.
Thank you very much, Amanda. Very interesting. I'm sure there will be some questions. Please place them in the Q&A, use the Q&A button. Maybe while we're waiting on that, I guess I have a very naive question. I mean, you did show the various different slide of the various different models, which I think have different like latitudinal and longitudinal dependencies. Some of them are quite sophisticated. Some of them are more just like spherically symmetric. I kind of would have like naively expected that it wouldn't be quite spherically symmetric, but more like kind of like a prolate ellipse or something like that. But where does the circular what is the argument for assuming circular symmetry for the halo?
I'm not sure if I have a great answer to that. I think mostly just because most of my knowledge of these repeaters comes from those papers. I would argue, so I guess it's an oversimplification to say that everything is spherically symmetric, for sure. Yeah.
Yeah, and then the next question is how turbulent is it? How much does it vary from line of sight to line of sight? Yeah. Okay, we do have a couple questions in the meantime. So Ryan Shannon asks, what do you predict for the DM halo towards the Magellanic Clouds?
So the Magellanic Clouds are, we have pulsar observations in there. So I think I actually don't know it off the top of my head, but I think we have a really good constraint in that way. You can just take the galactic latitude, subtract off this disk component, and then we have pulsars in both the small and large Magellanic Clouds, right? So you could get an exact value. I haven't calculated off the top of my head, but I'd be happy to kind of provide that info in Slack afterwards.
Okay, yeah, you can continue that discussion with Ryan in Slack. We also have a question from Susumu Anui, asking, could some of the inferred DM halo be attributed to the local group rather than the Milky Way halo?
Certainly. Yes, I guess we have no way of subtracting out other components. It's an upper limit in that way. And so I think if the local group is contributing a great deal, and it's since most of our fast radio bursts we detect are outside of it, it would definitely be convolved in the DMs we're seeing.
Yeah. Okay, we still have time for more questions if there are any, so don't be shy. I guess I had another question. So early in the talk, you said kind of the most conservative DM halo constraint from the M81 repeater was something like 52 parsecs per cubic centimeter. But why are you, I mean, later in the talk, you did bring it up. Why are you hesitant to just claim at least, say, like 10 parsecs per cubic centimeter halo contribution from M81? That still seems fairly conservative, right?
Yeah, I think there are really interesting arguments to be made about the particular. I guess it's just so the 52 number that I throw out is really just subtracting off the disk component, right? I think we do know a lot about that M81 burst, but then the argument kind of breaks down when we're extending it as a function of galactic latitude. So I think that's why I kind of want to not make these assumptions, but I think, yeah, especially because that for the M81 burst repeater in particular, that's been talked about in detail. Yeah, so I guess it's just like the if we're allowed to, or I guess if it remains legitimate to apply it as a function of galactic latitude.
Yeah. Okay.
But I do encourage any reader to attribute their own personal model to what they believe could come. Yeah.
Yeah. As long as they make their assumptions clear to the reader. Yeah. Okay. Then if there aren't any other questions, let's thank Amanda again for a very nice talk. And we will move to the last talk of the session, which will be given by Sunil Simha.
Can you all see my slides?
Yes, now we can. So Sunil is from the University of California, Santa Cruz, and we'll be talking about estimating the contribution of foreground halos to the FRB 180924 using its dispersion measure. So take it away, Sunil.
Thanks, Jason. Hello, everyone. Like Jason introduced, I am Sunil Simha. I am a graduate student at the University of California, Santa Cruz. I am working with Professor Xavier Pachaska, but also more broadly with the fast and fortunate FRB follow-up or F to the fourth team and the craft teams, of which I'm a member. And today I'm really excited to present some of our latest results on estimating the foreground contribution to FRB 180924's dispersion measure. So without further ado, let's get started. Now, this has been mentioned multiple times, even within this very conference, but I think it's worth emphasizing how amazing FRBs are as cosmological probes. They were essentially key to directly resolving the missing baryon problem, which was a lack of observational evidence for a large chunk of the low Z baryons, which were supposed to be found in the filamentary gas in the cosmic web. This famous plot from McCord et al. 2020 has been shown at least 20 times now, I think, probably around as much. But it essentially proved that the baryons are not missing, and they're indeed there because the measured DM cosmic, or the cosmic web dispersion measure of localized FRB sightlines are fairly consistent with the expected value from a lambda CDM universe. So this was a wonderful result, and it showed that FRBs can indeed be used as probes of ionized gas. They quite literally shed light on invisible matter. So that's the good stuff. And so when I first started working here at UCSC in my first year, I had a wonderful task, which was to study an FRB sightline in detail, and we got really lucky with FRB 190608. So this particular sightline was there within the SDSS footprint. The FRB itself was localized to this beautiful spiral galaxy at a redshift of 0.117. And so as part of two papers that we released, one led by Jai Chittiri, and the other led by myself, we were able to make a very detailed end-to-end study of the electron reservoirs in the foreground, starting, of course, with the Milky Way, halo, and the ISM, for which we used NE 2001 and Prochaska and Zheng 2019 halo model, and Jai Chittiri's work on the host galaxy itself, which looked at the ISM in detail and also the host halo. So my work was, the work that I led was more about the foreground halos and the cosmic web. So using the extensive spectroscopic information available to us in the SDSS, we were able to lay constraints on both the dispersion measure contributions from the halo gas of foreground galaxies, and also the diffuse filamentary gas in the IGM. So we were able to produce detailed reconstructions based on these spectroscopic redshifts, and we were able to make estimates of the individual contributions for the dispersion measure. So we found out that about a third of the dispersion measure comes from the FRB host and its halo, about a quarter from the Milky Way and its halo. Roughly 5 to 8% comes from the virialized halo gas of intervening halos. And finally, the remaining bit came from the diffuse IGM. So this was great because it was a proof of concept. We were able to independently estimate the dispersion measure of this FRB using purely optical observations, and we were able to compare it to the radio measurement, and we were able to say that the two of them are consistent with each other. Now, KG Lee has already mentioned in a previous talk that this is, of course, for one sightline, but with multiple sightlines, we can start laying better constraints on cosmological parameters like the fraction of baryonic gas that is present in the cosmic web, for instance. And also, even with individual sightlines, let's say there's a sightline in the future where there is a large discrepancy in the estimated dispersion measure and the measured value. So then we would be able to say something about some sort of interesting foreground electron reservoir that we haven't accounted for, maybe something like a group or the electrons in a galaxy group, for instance, or maybe something funky going on with the progenitor environment itself. So the possibilities are endless. This just opens up a whole new repertoire of tools to work with. Now, having studied the 190608 sightline in detail, it was time to move on to the next sightline, which we chose to be 180924. It was interesting for a couple of reasons. One, if you look at the location of this particular sightline in the McQuark plot, you notice that it is under the mean McQuark relation. And this means that it is likely, or it is possible, at least, that the foreground is somewhat underdense in terms of either halos or the diffuse IgM. And this is a hypothesis that we wanted to test. The other reason why this field is interesting was because it had basically very little spectroscopic coverage. So this represented a technical hurdle. So we had a Muse IFU observation of this field. So we had information within 1 arc minute of the FRB. So this is what our observation looks like. So this is on the left side, you can see the white light image. So basically, if you take the data cube and you squish it in the wavelength axis, this is the image that you get. So you see a lot of sources over here. The host galaxy itself is marked, it is over here, and the FRB is marked with the X. And you also get the spectra, of course. So from this data cube, we were able to identify quite a few background sources, and also two, most importantly, 2 foreground sources, which are marked over here, and the spectra are shown over here. So the foreground sources themselves were roughly 100 kiloparsecs away from the FRB sightline at their redshift, at their measured redshifts, both of them. And so, yeah, we had spectroscopic information, but nowhere as extensive as what we had for 1906-08. So all we had was essentially photometric data. So this particular sightline lies in the DES footprint. So we had UGRIZ photometry and also WISE photometry for some of the sources. So WISE 1, 2, 3, 4 magnitudes. So my idea was to try to use photometric redshifts to at least constrain the halo contribution to the dispersion measure. So in this talk, DM halos refers to the DM contribution from the foreground halos, not the Milky Way or the host halo. It's specifically talking about the foreground halos. And the idea is fairly simple. So what I have is, let's say you have this galaxy with multi-band photometry available. It is somewhere along the sightline, and maybe the halo intersects the sightline just a little bit, maybe a lot, who knows. So using this photometry, I can estimate the PDF of the photo Z using some software. And the goal is to convert this PDF of photo Z to a dispersion measure PDF for this galaxy. And repeating this exercise for all the galaxies within our field, we can then start laying constraints on the total DM halos. And so this is the algorithm or the methodology that we came up with. Fear not, I will not go through this in full detail. I'll just go through it very briefly. So basically start with the photo Z PDF, and you come up with photo Z realizations from the PDF. So for each realization, we can then produce a probability density function of a stellar mass for the galaxy. So the stellar mass estimate is produced by SED fitting using another software called SIGAL. And with each stellar mass realization, we can produce a halo mass PDF. So basically, we're translating the photo Z information to halo masses of the foreground galaxies. And using a halo gas model, in this case, we used the one from Prochaska and Zheng 2019, also the same that we had used in our previous paper. And we are able to come up with a PDF of the DM of that particular galaxy. Combining all the galaxy PDFs, we can produce a final PDF of the DM produced from only the galaxies with photometric data only. And so this is what...
About 3 minutes, Sunil.
Okay, thank you. This is what the distribution looks like. So this is the Muse field of view over here, but the broader field is the DES R-band image. And so the blue squares over here mark the foreground galaxies dispersion measure contributions. So you can see that they're the average values basically. And you can see that they're fairly small, each of them. And together they add up to roughly 13 parsecs per centimeter cube. Now we also took the galaxies with spectroscopic data, or the spec-Zs, and if we look at the PDF of the dispersion measure with the combined spec-Z and photo-Z sample, this is the PDF that we get for the DM halos, and it's the mean is roughly 21 parsecs per centimeter cube. This is altogether, if you compare it to the average value of DM halos for any random sightline, you can estimate using a halo mass function, for instance, you will notice that this is fairly small. In fact, it is about 5 times small compared to the Amulus halo mass function and the Planck lambda CDM cosmology. This is consistent with the expected the DM cosmic that we think we should get. So if we just subtract the Milky Way and the host contributions from the FRB dispersion measure, this is that's the red point over here. So here I'm plotting the DM cosmic. You can see that it is below the McCart relation, which is in the dotted line. And this is our prediction, or this is our model value for the cosmic dispersion measure. Here we're cheating a little bit. We don't really know the DMIGM. We're just assuming this is like any average sightline, which is not true, of course. It could be more or less. We need to do a full analysis for that, which will require spectroscopic redshifts, but that is what it is for now. Coming to the results, so basically we showed we have now a new approach to estimating DM halos where spectroscopic data is limited. So that's a win. For this particular sightline, we were able to show that there's no foreground halo intersecting the sightline less than roughly 100 kiloparsecs, which is why the DM cosmic for this sightline is low. One would consider this particular sightline something typical in the universe. So if you look at the location of the sightline on the McCart relation plot with the PDF of the DM cosmic plotted on top, you can see that the particular sightline 18924 lies close to the median value of the DM as opposed to the mean. So the median is at a lower value. So this is considered fairly typical, and we expect to see a lot more sightlines like this in the universe. This plot is part of a future work that I'll be working on in the next few months. This is basically pointing out the fact that there are a lot of FRB sightlines which are seemingly above the McCart relation, whereas we expected them to be below. And so something interesting could be happening in these sightlines. Most likely reason, of course, is that we have underestimated the host dispersion measure, but it's also possible that there is some foreground overdensity, maybe some group or cluster or something like that, at least in some of these fields, and that is something that we intend to investigate. This will tie in with the FlimFlam project, as KG Lee had already mentioned, and it would also help in constraining some of the cosmological parameters that he mentioned earlier. So with this, I come to the end of my talk. Thank you for your patience, and I'm happy to answer any questions.
Thank you very much, Sunil. Yeah, we definitely have time for questions, so please post those in the Q&A. All right, we have a couple questions already. The first is from Moet. It's a long one. Nice talk, Simha. I have two questions. The first one is, as we know that the DM halo contribution is greatly influenced by the chosen halo profile and assuming baryon fraction and assume baryon fraction in the halo, I'm curious if you account for the uncertainty in their values when calculating the PDF of DM halo.
Right. So in this, okay, let me go back. So over here, the uncertainties that we account for is basically the estimate, the uncertainty in the stellar mass of the galaxy, and also the uncertainty in the stellar mass to halo mass relation. So we don't really account for the uncertainty that would come into play if we had different models for the halo gas distributions. But we can say that, so you can do a back of the envelope calculation. And if you look at some of the distributions in Prochaska and Zheng 2019, for instance, you can say that, you know, the halo gas dispersion measures will be can be a factor of 2 higher, for instance. Even then, we can say that the dispersion measure from halos for this particular sightline is indeed less than average, and it's nowhere close to explaining, well, it still implies that this is a sort of underdense sightline as far as number of halos is concerned, or the halos closely intersecting the sightline is concerned.
Okay,
that answers your question.
We'll take first a question from Susumu Inui, who asks, Prochaska and Zheng discuss a wide range of models for the gas distribution in halos. Does the data favor some models over others?
So we haven't really, like I said, we haven't really investigated the different models, but as of now, let's see. So the one way we could say one or the other model is favored is by looking at the DM cosmic prediction from a particular model, let's say, and comparing it with whatever we have measured. So for this particular model, we can see that it is a slightly lower, but it's still consistent. But if the problem with doing this is that we don't really have a good sense of DMIGM. In this case, we're just using the average DMIGM for any particular sightline. It doesn't really take into account the fluctuations or the cosmic web in this sightline itself. So maybe in the future, once we have full spectroscopic coverage, which as KG Lee pointed out, we sort of do, we can probably lay more constraints on which models are better for this sort of work.
Okay. We'll take a second question from Moet, who asks, I'm curious whether you've done any work on R2, where the DM excess is 70 to 100 parsecs per cubic centimeter. Therefore, likely it is a nearby source, for which Lee et al. Claimed that the IGM contribution to the FRB sightline could be significant, leading them to conclude that the FRB should be within Z is 0.05.
Yes, so I haven't done it yet, but it is certainly, I think, on the list of sightlines to be examined. So this will be part of the XSDM project that I'll be working on in the next few months, and I'll be curious to see what comes of it for that, for R2 in particular.
Mm-hmm. This plot that you have up right now, does it agree with, I mean, there was a recent CHIME catalog paper in which they found some significant number of FRBs seem to have a kind of largish, something like 400 parsec per cubic centimeter local contribution. Is that consistent with what you're seeing here?
Well, we need to be careful. This is a very preliminary plot. And many of these FRBs over here do not have a good host DM contribution. or even a local DM contribution for that matter. Essentially, we're assuming a lot of the host DMs are 50 divided by 1 plus Z host. So I think a more detailed imaging and spectroscopic analysis is required before I can make any comments in that regard. But yeah, it's still work in progress for now.
Okay. Well, thanks again on behalf of all of the participants, and thanks to all of the speakers for the excellent talks that we've heard in the last couple hours. It's time to round up the session. Moet apologizes for the long questions. Thank you very much, Moet. I appreciate your apology. And we'll end the session here. And just a reminder once more that we'll meet if you want to for coffee and tea in Gather Town right now. Thank you all. And the next session starts in a couple hours.